Dear students, in this video we will start electric motor subject module 3 performance of three-phase induction motors. First we will see syllabus. In this module 3 you are going to learn about phasor diagram of induction motor on no load and on load, equivalent circuit, losses, efficiency, no load and blocked rotor test, performance of the motor from the circle diagram and equivalent circuit, cogging and crawling, high torque rotors. So we have two type of high torque rotors in induction motors. One is double cage and deep rotor bars, equivalent circuit and performance evolution of double cage induction motor working as induction generator. So this is the module 3 syllabus, and we will discuss phasor diagram of induction motors. So before phasor diagram, so we have two devices, transformer and induction motor. So consider these two devices. Transformer is static device and induction motor is a rotating device. So induction motor phasor diagram is similar to the loaded transformer. So both the devices of phasor diagram will be equal, since transformer will have two type of windings, primary winding and secondary winding. Even induction motor will have stator winding and rotor winding. In primary winding in transformer is similar to the stator winding in induction motor, and secondary winding in transformer is similar to the rotor winding in induction motor. So the only difference is here, secondary of induction motor is rotating, secondary winding is rotating in induction motor, and short circuited, while transformer secondary winding is stationary, secondary winding of this transformer is stationary and secondary winding is connected to the load. The load on induction motor is mechanical while loaded on transformer is electrical. So induction motor is loaded but mechanically loaded, but transformer is electrically loaded. Still, by finding electrical equivalent and of mechanical load on the motor, the phasor diagram of induction motor can be developed. So phasor diagram of the induction motor, if you are developing, before that we need to consider the some of the parameters. First we will consider pi. Pi is equal to magnetic flux links with both primary and secondary windings, and self-induced EMF is E1. So E1 is the self-induced EMF in the stator, and E2R is the induced EMF in the rotor. R1 is equal to stator resistance per phase and X1 is equal to stator reactance per phase. The stator voltage per phase V1 has to counter balanced self-induced EMF. So counter balanced self-induced EMF E1. So stator voltage per phase is V1 and balanced self-induced EMF is E1. As supply voltage drop is V1, supply voltage is V1, the voltage drop is I1 into R1. Due to the reactance, drop is I1 into X1. So on stator side, so we can write V1 is equal to minus E1 induced EMF in stator plus drops I1 R1 plus J I1 X1. So now we will simplify by taking the common I1. So from the equation I1, if you take R1 plus J X1 you will get, so J X1 is impedance Z1. So now we have some steps to draw the phasor diagram. So before that, rotor induced EMF E2R. So E2R also similarly we can write in terms of drops, resistance drops and reactance drop. So I2R R2, that is a resistance drop, and I2R X2, that is a reactance drop. So totally I2R R2 plus J into X I2R X2. So by taking the I2 common, I2R into Z2R. Now the value of E2R, so is the so what is the E2R is rotor induced EMF in the running condition. So it depends on the ratio of rotor turns to stator turns. So the value of E2R depends on rotor turns to stator turns. The rotor current in the running condition is I2R. The rotor current uh, in the induction motor is I2R, and it is lags E2R by an angle pi 2R. So power factor angle pi 2R. The reflected rotor current I2R dash on the stator side is affected on load and given by. So here we are writing the rotor current in terms of turns ratio. So turns ratio we are taking K. I2R dash is equal to K into I2R. The induction motor draws no load current. So no load current is I0. So here no load current is I0. So which is phasor sum of IC and IM. So IC and IM we have two currents. So this is the phasor sum of IC and IM if you take, that will be equal to no load current I0. So now the stator current, the total stator current drawn from the supply I1 is equal to I0 plus I2R dash. Now pi 1 is the angle between V1 and I1, and cos pi 1 gives the power factor of the induction motor. So thus using all above relations, the phasor diagram of induction motor can obtain. The phasor diagram of induction motor can obtain. Right. So now we will see the steps to draw the phasor diagram. Here we have a 10 steps. So using these 10 steps, we are going to draw the phasor diagram. So take pi as the reference phasor. So here pi is reference phasor we have taken in x axis, and the induced voltage E1 lags pi by 90 degrees. So here the pi by 90 degrees. So minus E1 by reversing the voltage phasor. So this is a minus, opposite to E1 if you take, that will be equal to minus E1. Right. The phasor E2R is rotor running induced EMF. E2R is in phase with E1. So E1 and E2R, if you take, that will be both are in phase with each other. So I2R shows the lagging E2R, that is E1 direction by pi 2R. So here, so E2R is lagging I2R shows lagging by E2R by some angle pi 2R. So here pi 2R here mentioned. Show that pi 2R into R2. So pi 2R into R2 drop in phase with I2R. So both will be in phase with pi 2. Next one, pi 2R into X2R. Pi 2R into X2R leads the resistive drop by 90 degrees. So this is the inductive drop or reactance drop. So it will leads the by 90 degrees to the drop across the rotor resistor. So rotor resistor drop is I2R into R2. To get exact location of to get exact location, so we can take 90 degrees here and reverse pi to r to get I to r dash here. So pi to r, if you reverse, if you take I to r, you will get. Now Im, magnetizing component current, so is in phase with the pi, and Ic is the leads with respect to Im, magnetizing working component current is Ic, so it is leads the magnetizing current Im. So if you add Im and Ic, Phasor addition, if you take Im and Ic, you will get I0. So that is no load current on stator. And add I0 and I2R dash, you will get I1. So I1 is here. If you add these two, if you add these two values, so I2R and these values, if you add, you will get I1 here. From the tip of minus E1, so is here minus E1. So I1 into R1, stator resistance drop is in phase with I1. So in phase with I1. So these two lines will be, so this I1 and I1 R1 dash will be parallel. Now reactance drop, stator reactance drop X1, I1 X1, so at an angle 90 degrees, leads the 90 degrees. So V1 get phasor, so to get V1 we need to add, so this drops minus E1 and I1 R1 plus I1 X1, if we add, we will get supply voltage to the stator. So the angle between V1 and I1 is pi. So here pi is here. So you are considering. So according to these steps, so we will draw the phasor diagram of induction motor. So it is similar to the working transformer. So here we can also call induction motor as a rotating transformer. Okay, so this is the another name of induction motor. Induction motor we can also called rotating transformer. Okay, so next video we will see equivalent circuit of induction motor. Thank you everyone.